Okay, hi everyone, welcome back to this video series for our introduction to firewalls, stateful packet filtering. So far, we have only looked at stateless packet filtering. Modern firewalls use a more robust version, which is called stateful packet filtering. With stateful packet filtering, the firewall remembers state about expected return packets. Any unexpected packet arriving at the firewall claiming to be a solicited response is blocked immediately. When an IP packet is a request for information such as an HTTP port 80 request to a public website, the IP packet lists its return IP address and an unused return port number greater than 1023, for example, 2065, to which to deliver the response. If the firewall knows only stateless packet filtering, it doesn't know that a packet will arrive shortly on port 2065. The only choice that a stateless packet filter firewall has is to leave all ports greater than 1023 open for all traffic. A hacker can easily use this opening to initiate communication with internal computers and ports greater than 1023. The firewall will pass this unsolicited traffic. Stateful packet filtering blocks all traffic on ports greater than 1023 and allows only network traffic that matches the response port of a previously sent IP packet. The firewall internally maintains a table of information on which ports it may expect traffic. If the firewall determines that a communication exchange is finished, it removes that information from the table. In cases where the firewall is unable to detect that the communication has ended, it automatically removes that information after a short time period. The doorman guarding the headquarters at Legal Inc. is stateful too. Rarely is a visitor allowed to enter without an appointment. Doorman Sam will most likely have a dated list of expected visitors and not rely on a spoofed appointment. Confirmation later carried by the visitor himself. Movies make you believe that wearing overalls and pretending to be a toilet repairman seems to do the trick. Wearing balloons and implying that you came to do a surprise serenade is also classic. Think of the delivery guy rolling in ordered supplies. He doesn't know who ordered it. He just knows to deliver it at the front desk, which is similar to the network address translation, NAT functionality that we look at next. Network address translation, NAT. Originally, network address translation, or NAT, was introduced to save IP addresses in use on the internet. An IP address is 32 bits long, and with that number of bits, you can have only about 4 billion different IP addresses because many companies have claimed large blocks of IP addresses. The available IP numbers were quickly becoming depleted. In May 1994, RFC 1631 suggested what was then thought to be a short-term solution, NAT. As it turned out, NAT offered several unexpected advantages, as you will soon discover. With NAT, all computers on the internal network can use a private range of IP addresses such as 10.0.0.0/8, which is not in use on the internet. When they make a connection to the outside world, the NAT computer replaces the private IP address, for example, 10.65.1.7 listed as source IP address in the IP packet, with its own public IP address, 23.1.8.3, and sends the packet on its way. The destination computer on the internet thinks the original sender is 23.1.8.3 and sends a return packet back to this IP address. The NAT computer receives a packet for 23.1 10.8.3 and replaces the destination IP address with the original 10.65.1.7 to travel the last leg on the internal network as shown in figure 3.2. NAT may as well have been called network address replacing. Why does NAT save IP addresses? Because NAT never exposed the 10.0.0.04/8 IP address on the internet. Many companies can use the same internal private IP address range of IP addresses and only need a single or a few public IP addresses. The computer on the internal network never noticed that NAT took place. The destination computer on the internet didn't notice NAT was involved either. So how did the NAT computer know to send the returning address to 23.1.8.3 back to the original sender 10.67.1.7? Just as stateful packet filtering keeps a list of expected return packets, NAT also keeps a list of which addresses to replace with which original address. These are called NAT mappings. Finally, what if more than one computer on the internal network wants to use the NAT computer to communicate with the internet? The 1994 RFC 1631 document proposed to solve this by letting the NAT computer have multiple public IP addresses and using one for every concurrent connection from the internal computers to the internet. In every modern implementation of NAT, this can just be as easily be solved by not only changing the source IP address to 23.1.8.3, but by replacing the source port number with an unused port number above 1023 as well. All the NAT computer has to do is keep a list of which port number temporarily belongs to which requesting internal network computer. Technically, the technique to replace ports is called network address port translation, NAPT, but everybody just says NAT. Nearly 65,000 port numbers are available, so in theory, one NAT computer can handle thousands of internal network computers. Security aspects of NAT. Although saving IP addresses is cool, NAT also has a security aspect. As a byproduct of replacing the original IP address, NAT hides the true IP numbers in use on the internal network, which is a big advantage. The possibility of hiding the actual IP address is also the reason that almost all firewalls can do that. The outside world will only see the outside public IP address of the firewall and will never learn the internal IP addresses. Even if a hacker knows the internal private IP address, they are not nearly as interesting to him as the internal public IP addresses that would have been used without NAT. Private IP addresses such as those in the 10.0.0.04/8 range can't be routed over the internet. ISPs actively block those addresses if used on the internet. Thousands of companies use 10.65.1.7 internally, so it isn't possible to decide where an IP packet with that IP address needs to go on the internet. If the firewall circles, people tend to see NAT more as a security precaution than as a method of saving IP addresses. The term IP masquerading is often used for NAT, which emphasizes the hiding aspect of NAT. NAT does nothing to protect the computer on the internal network. If the computer is tricked into making a connection to an untrusted computer on the internet, the NAT component happily shuttles the introducing packets back and forth. A firewall should always combine NAT with stateful packet filtering. You normally don't have to do a lot to let NAT do its work, unlike packet filters, which have to be defined for every protocol or the service that you want to allow. Now is largely an automatic function of a firewall in the description of NAT, which concentrated on network traffic that was initiated by computers on the internal network. It's also possible to use NAT when computers on the internet initiate network requests. Consequences of NAT. The use of NAT has some drawbacks, and although they don't outweigh the advantages of using NAT on our firewall, it's worthwhile pointing them out. The NAT computer is effectively doing IP spoofing, although we usually don't call it that if it is the firewall that does the spoofing as opposed to a malicious hacker. A hacker in a NAT-protected network is harder to pinpoint from the outside. It appears that all network traffic is coming from the firewall doing NAT. The log files created by the firewall may help to determine who was using which port at what time, but this is certainly harder than having directly obtained the unique IP address from the hacker computer. Masquerading IP addresses has its disadvantages. Some network protocols list the original source IP address or source port number in more places than the IP packet itself. This is normally not a problem, but if the firewall wants to automatically replace all the occurrences of the numbers that should be hidden, it should know exactly where these protocols list the numbers and change them accordingly. Most NAT implementations support changing the IP numbers in a couple of well-known protocols that need this change. The best known examples are the FTP protocol and the ICMP protocol. For other protocols that are not supported, you either have to install routines that do this so-called NAT editors, or you are unable to use them through the NAT firewall. If the sending computer encrypts the IP header of a packet, or if the data of the packet itself is encrypted and contains the IP address as well, the firewall may not be able to make the necessary changes to the IP header or the data inside the packet. Encryption is used to protect the IP packet from deliberate changes made by intermediate snoopers on the network. It makes sense that the firewall won't be able to make those changes. Either solutions for this problem are not readily available. Installing additional NAT editors won't help much. Of course, those routines won't know how to decrypt those packets either. Ongoing work on standards for allowing IPsec encrypted data through a NAT firewall is almost finished. Some multimedia and conferencing protocols want to create independent back channels to the sender of a request. Doing so causes problems with stateful packet filtering, but NAT may have trouble with these kinds of protocols as well. Depending on the firewall, you may be able to create packet filters that specify the expected ports for the return channel, or you can install a special application proxy as discussed in the next section. Application proxy. Besides stateful packet filtering and NAT, another function of a good firewall is the application proxy service, sometimes called application gateway. Consider an application proxy as an elaborate version of a packet filter, whereas a packet filter is capable of inspecting data only in the lower levels of an IP packet, such as the IP address or port number. An application proxy is capable of inspecting the entire application data portion of an IP packet. An example is an FTP application proxy that can scan FTP packets for certain file names and block the requests if needed. An application proxy plays roles of a liaison officer. The internal network computer sends a particular internet request to the firewall. The application proxy of the firewall picks up the request, inspects the entire packet against rules configured by the firewall administrator, and then regenerates the entire internet request before sending it to the destination server on the internet. The firewall appears to have sent the request. The return result will again be inspected, and if the rules allow the result to pass, the firewall will build a response packet and send it to the internal network computer. The following are two important distinctions between packet filters and application proxies. A packet filter inspects only the packet header, whereas an application proxy can scan the entire application data in the packet. A packet filter passes an allowed packet. The same packet travels from the internal computer to the server on the internet. An application proxy regenerates an allowed packet. A new packet is built and sent from the firewall to the server on the internet. A similar strategy is used on the return packet. The application proxy maintains two separate connections. One connection is between the application proxy and the internal computer, and the other connection is between the application proxy and the internal computer. An application proxy service on a firewall offers several advantages. The application proxy can inspect the entire application of the IP packet. This inspection happens both when the internet request is sent and when the reply packet from the internal server is returned. Because the application proxy understands the application protocol, it can create a much more detailed log file of what is sent through the firewall. Packet filter log files know only about the packet IP header information. The internal computer and the server on the internal never have a real connection. Instead, the firewall regenerates every packet that is sent between the two. This means that problems or attacks associated with buffer overflows or illegal conditions in the packets never reach the internal computer. An application proxy actively sends newly created packets on behalf of the original sender. It doesn't route packets between the network interfaces. If the application proxy or a firewall were to crash, the communication connection would cease to exist. With just a packet filter approach, a crash of the firewall may result in packets being allowed to route through. An application proxy can inspect network traffic that uses multiple connections. Packet filters don't recognize that separate connections to the same application belong together. Because the application proxy looks at the entire application data, it can store return results such as content of web pages in cache. Subsequent requests for the same information can be fulfilled from the cache instead of having to fetch the same content repeatedly. Although many people associate a proxy with this caching function, it is a secondary function from a security standpoint. Unfortunately, application proxies have some distinct advantages as well. Proxy per application. The application proxy service needs to understand the application protocol used. This means that the firewall should have a specific application proxy for every network application. Most firewalls support a proxy for common applications such as FTP and HTTP, but for other network applications, you may not find a suitable application proxy. In that situation, you can't use the application proxy function for these network applications. Required proxy configuration. For some application proxies, the internal network computer may need to be aware that it is actually connecting to the application proxy instead of directly connecting to the server on the internet. Internal network computers that want to use these application proxies require a configuration change. This is called a classic application proxy by RFC 1919. If a computer on the internal network can use the firewall application proxy without doing any special configuration, RFC 1919 calls this a transparent application proxy monitoring and logging. Why would you need to do extensive logging if you configured a firewall with packet filters, made sure that NAT is hiding the private IP addresses, and implemented application proxies that separate the internal network from the internet? Good question. It's true that a carefully configured firewall provides security for your internal network, but you still need to be sure that you don't overlook anything. That's one of the reasons why you want to have the firewall log every connection it makes and every packet it blocks. You want to verify whether the firewall is really as secure as you believe it to be. Here are 4 good reasons to let the firewall create extensive logs of everything it does. Report usage. You want to aggregate the information in generated logs to have an indication of the firewall's performance, usage and statistics, and perhaps even do accounting and charge users for the service. Detect intrusion. It is bad enough if the hacker infiltrated your network. It would be worse if you didn't know about it. The longer a hacker can linger on the network, the more damage he can do. Frequent inspection of the log files can reveal suspicious patterns or even show the evidence of a successful intrusion on your network. Discover attack method. Even if you detect an intrusion, you still need to be sure that the hacker is stopped and he can't repeat the attack that he staged before. This requires a careful analysis of all log files. Hopefully, you will spot how the hacker was able to enter your network and also when he first entered your network. Such information reveals possible Trojan horse applications that may have been left behind earlier, or the invalidity of backups made after the fact. So I'm going to leave here to see this video. If you like listening, please consider like, sharing and subscribing, and thank you for spending the evening with me.